Okay, so this is a document that was released by Alberta Education in 2017. So it's released items, which that means that they're questions off previous diploma exams. Okay, so give you an idea of maybe some of the different types of questions that maybe we haven't seen already that you would see on the exam. So there's a breakdown on the next page. It has the key, the answer, which topic it is. So RNF stands for relations and functions. Like I think, if I remember correctly, that's 58% of the exam because that includes transformations, as well as the standard, whether it's acceptable or excellence level question. So let's start going through this. If f at x equals x minus 2 all squared plus 1 is transformed into the graph g at x, which is equal to f at x minus 4 plus 3, then where will the coordinates of the vertex on the graph of g at x be? So that original equation is an equation in vertex form. In 20-1, you learned about the vertex form of a quadratic. It was y equals a bracket x minus p all squared plus q. You might remember that we used a process called completing the square to go from general form into this vertex form. But what it told us where the vertex of the quadratic was. It was found by the values of p and q. A determined the direction of opening, whether it was positive or negative, and it also caused a vertical stretch, just like it has been doing throughout this entire course. But the values of p and q tell us the vertex. Notice the general form is x minus p. So, like we've been doing with our h value, it's hooked directly onto the x with a plus or minus. This is exactly the same. It was the opposite value of what it appeared to be. So for the quadratic f at x, our vertex would be at 2, 1. And now it's going to be transformed. So g is f at x minus 4 plus 3. So that would be an h value of positive 4 and a k value of positive 3, which means it's going to go 4 to the right. And if you're at positive 2 and you add 4, you'll get positive 6. And you're going to go 3 up, which means you'll add 3 to the 1 and get positive 4. So that's why C was the answer. That's the new vertex. Next question. You have a partial graph of y equals f at x. Which of the following transformations will always create invariant points at A, B, and C? So A, B, and C are the x-intercepts. And there's two transformations that would not change those. One of them would be stretching it vertically about the x-axis. Those points are 0 units away from the x-axis, so that distance, no matter what the stretch factor is, will not change. The other thing that would happen is if it's reflected over the x-axis. That wouldn't change those invariant points either. So, equation A is a horizontal stretch. That will change the x-intercepts. Equation B is a vertical stretch. So that one will not change the x-intercepts. Will not change the x-intercepts. Okay? Now, the word always is important there because in the case of question C, if k is 0, then that won't change the invariant points. And same thing with answer D. If h is 0, that would not change the invariant points. But no matter what vertical stretch factor you have, it will not change the invariant points on the x-axis. Right, so that's why B was the answer. Part C. When compared to the graph of f at x, the graph of 8y equals f at negative x has been reflected in which axes and vertically stretched about the x-axis by a factor of what? Well, to do that, you would want to get y by itself. So if you start with 8y equals f at x, f at negative x, I should say, and to get y by itself, you would divide both sides by 8, which is the same as multiplying by 1/8. So the fact that a is 1/8 means that it'll be a vertical stretch by a factor of 1/8. So that eliminates a and c because those show vertical stretches by 8. And because b is negative, that's a reflection about the y-axis. So that's the reason that answer B is correct. Okay, on to the next page. The graphs of f and g are shown below. Each function is then horizontally stretched, and we actually saw this one already once before in one of our review packages. Each function is then horizontally stretched by a factor of 2 about the y-axis, resulting in the new functions p and q. The domain and range of each new function are found in the table below. So, for the first one, the first graph, if you horizontally stretch by a factor of 2 about the y-axis. So what will happen there is that this starting point, which is 2 units to the left, if it's horizontally stretched by a factor of 2, it'll be at -4. So I think the one we saw in our review started with the same graphs, but I think there was also a reflection as well, which isn't happening in this case here. But if you horizontally stretch by a factor of 2 about the y-axis, this value of -2 is multiplied by 2, it'll become -4. The y-intercept will be invariant, okay? And this graph would look something like this. Something like that. And so the domain of that will be still, or will change, I should say. It'll go from -4 to positive infinity. The range will go from 0 to positive infinity. Okay? So for the first one, we just want to know the domain of this graph, which will be x is greater than or equal to -4. And then for the second one, we want the range. Well, if we horizontally stretch that by 2, again, that point will go from -2 to -4. This point, which is at -1, will go to -2. Sorry, this number is 3 here, and then the range of this one would be greater than or equal to 0 still. So that would be 5. So that's that one. Now again, if the second graph is horizontally stretched by a factor of 2 about the y-axis, so I've got 2 of the points stretched, I just have to do this one here. When x is -3 times 2 is -6. And this point is off just a bit. Move it over. And then here's our new graph. Okay, it'll go like that. And like that. So the domain of that has not changed. It is all real numbers. So that will be number 4 in that list. And the range of this did not change either. It will be that y is greater than or equal to -4, which is number 7 in that coding. We're just going through this 2016 released items book. Right, so that would be the answer to that. Number 4, the graph of f at x is transformed to g by that transformation. So we got 2 transformations there. Let's first deal with the fact that a is -1. So when you introduce an a value into an existing equation, it's a times f at x. The entire function is multiplied by a. In this case, the entire function will be multiplied by -1. So it'll be -4x squared minus 3x plus 5. So that's the first step. That's dealing with an a value of -1. And then we have a b value of -1 as well. So now we're going to do negative f at negative x. And to do that, the x is replaced with negative x. Whatever happened to the x before also happens to the negative x. And so for that first term, it means it's going to be squared. Then you're going to have -3 times negative x plus 5. And when you square negative x, it becomes positive x squared times -4 is -4x squared. But the second term, -3 times negative x, is positive 3x. And that is why C is the correct answer. A is multiplied by the entire function. X is replaced with bx. And whatever happened to the x before happens to the bx as well. So the next question, students asked to draw the inverse of the following graphs. If no additional restrictions are given, which 2 graphs will have an inverse that is a function? So you might remember we use something called the horizontal line test on a function to see if the inverse will also be a function. We use the vertical line test on the original function to see if that is, but for the inverse, we use the horizontal line test. If a graph passes the horizontal line test, its inverse will pass the vertical line test. So for graph 1, no matter where you draw this horizontal line, it'll only cross the graph in one spot. So graph 1 passes the horizontal line test. That means its inverse would pass the vertical line test. So we know graph 1 is one of our answers, so we can cross off C and D. If we move this horizontal line over to graph 2, it can fail the horizontal line test, which means that it would fail the vertical line test. So graph 2 is not correct, so now we only have B left, which says that's graph 1 and 3 will work. Graph 3 does pass the horizontal line test. Graph 4 does not. You just have to find any spot where it fails that test, and that's what you're looking for. So this confirms that the answer is B, graph 1 and graph 3. Next question. Student was asked to solve that equation using an algebraic process. She's able to simplify the equation into that form as a quadratic. What is the value of C if you write the equation as a quadratic? So there's some work that we're going to have to do here, and that will involve making the bases the same. So the top, which is 125, a base of 125, can be written as 5 cubed to the power x squared plus x. So I just multiplied out the x bracket x plus 1. And on the bottom, I've already got a denominator, or a base of 5, I should say. So that one's good. But on the right side, I need to write the 25 with a base of 5, which would be 5 squared, to the x minus 5. So we've got 5 to the 3x squared plus 3x over 5 to the 3x minus 4 equals 5 to the 2x minus 10. So on the left side, we can simplify. You're dividing powers with the same base. That means we can subtract the exponents and keep the base the same. Have to remember we're subtracting the entire binomial of 3x minus 4. And we put it in brackets because of that, which is important because the minus sign in front of the bracket changes all the signs inside. So we have 5 to the 3x squared. So that's going to become 3x minus 3x, which cancels. And the negative in front of the bracket will make the negative 4 a positive 4. And now we have both sides expressed as a single power with the same base. This is an equation. Using the principles of equations, if the bases are equal, the other parts are equal as well. The exponents will also be equal. So the 3x squared plus 4 will equal 2x minus 10. And then we want to write a quadratic equal to 0. And this is where we'll get our answer from. So we're going to subtract the 2x from both sides, and then we add 10 to both sides. We get plus 14 equals 0, and that's the number we're looking for. The value of c, the constant, is plus 14. So C is the correct answer. Okay. Next page, the point A, 3 comma negative 5 lies on the graph of y equals f at x. The ordered pairs below represent possible coordinates of the new point corresponding to point A after f at x undergoes a single transformation. So you got 6 points to choose from. Now the first transformation is that the graph is reflected about the line y equals x. Remember, that means the inverse. And to get the inverse, you interchange x and y. So the point 3, negative 5 will become the point negative 5, comma 3. When you reflect the graph over the line y equals x, that is the inverse. And to get the inverse, you interchange x and y. So negative 5, positive 3, that's point number 5. So the next thing we're told is that f at x is reflected about the line x equals 0. Well, the line x equals 0 is the y-axis. If it's reflected over the y-axis, you change the sign on x, the y value stays the same. So it'll become negative 3, negative 5. Instead of being 3 units to the right of the y-axis, now it's going to become 3 units to the left. Reflects over the y-axis. So negative 3, negative 5 is 0.3. Our last transformation, the graph is reflected over the line y equals 0, which is the x-axis. So now the y component will change its sign. The x value will stay the same. The y component will change its sign. Instead of being 5 units below the x-axis, it'll now be 5 units above. So 3 comma 5, which is 0.1, and your code will be 531. Remember, there are 4 boxes for numerical response, and you always work left to right. But the computer marks what you bubble in below. So again, you have 6 hours. Take the time to go back and check all your bubbles. Multiple choice and numerical response. Number 3, I think we saw a question very similar to this in one of our reviews. You're told what log base a of 8 equals and log base 4 of b equals. What is the value of log base a of b plus log base b of a? So you need to find out what a and b are. If we take the fact that log base a of 8 equals 3, and we want to find the value of a, that can be done by starting with the base and cycling through. It'll be a cubed equals 8, and then to find out what a is, we take the cube root of both sides, and a equals 2. We'll use the second expression to find out what b is. Log base 4 of b equals 3 halves. So again, starting with the base and cycling through, again, that's a b, not a 6. You will get 4 to the power 3 halves equals b. And power 3 halves means square root cubed. So it's a square root of 4 cubed, which is 8. So that's what b is. So now we want to find the value of log base a of b plus log base b of a. And round to the nearest hundredth because the second one's going to be irrational. Log base 2 of 8 is 3. That's asking 2 to what power is 8. But to find out what log base 8 of 2 is, we need to use our calculator. Log base 8 of 2. 0.3 repeating. So it'll be 3.33. And so remember that you have the options under box 2 and 3 for a decimal. So that decimal would take that second box and you have to bubble the decimal below. Okay? An expression equivalent to that, where x is between 0 and 90, is what? So sometimes they'll do this, where they combine, two different outcomes, completely different outcomes, where you're involving a logarithmic function and a trig function. So we need to simplify what's inside the brackets, and that can be done by using the sine 2x identity. So on top we have 2 sine x. On the bottom, sine 2x is 2 sine x cos x. And what happens then is that the 2 sine x's cancel. You divide top and bottom by 2 sine x, which will leave us with 1 on top. So that will give us log of 1 over cosine x. So that's not one of the 4 choices that we have. So we need to do something else. 1 over cosine x is the same thing as the log of cosine x all to the power negative 1. Which, from that, you can use the power law and the negative 1 can come in front. So it's negative 1 times the log of cosine x, which is answer B. So sometimes they'll do that where they will combine 2 different topics. Number 4, log base a of b is 1.26, where a and b are greater than 0, and a can't equal 1. What is the value of log base a of the cube root of b? Well, log base a of the cube root of b will be log base a of b to the 1/3. Write it as a power instead of a radical, and then the power can come front. So you're going to have 1/3 log base a of b, and we are told that log base a of b is 1.26. So we're going to multiply that by 1/3, which is the same as dividing it by 3. So the answer is 0.42. exactly. So again, in this case, you would fill up all 4 boxes. 0.42. Decimal will be in the second box. You'd have to bubble in the decimal in the second column below. This next question, based on this graph, the partial graph of a logarithmic function in the form f at x equals a log base b of x minus h, where b is greater than 1, is shown below. So produce this graph, the values of a and h in the function must satisfy what? Must satisfy what? Well, if you look at what the graph of a logarithmic function looks like, start with that as a starting point. So if we just go y equals log of x as a reminder to what this graph looks like. So zoom 6 to set my windows to their standard settings. That's what the graph of a logarithmic function looks like. As you go left to right, it's rising. Calculator doesn't do a good job of showing it here. If I choose zoom decimal instead, it's a little bit better, but it actually that has no minimum value. The y-axis is an asymptote. The graph just keeps going down to negative infinity, getting closer and closer to the y-axis as it does. But this graph is rising as you go left to right. The graph that we're looking at does the opposite. It falls as you go left to right, which means that it had to have been reflected over the x-axis, which means the first thing we can say is that a has to be negative. So we can cross off C and D. The second thing that has happened is that the asymptote changed from the y-axis. It's gone to the right. So our h value, it has to be positive because it's going to go to the right. And that is why A is the correct answer. If h was negative, then the graph would be on the left side of the y-axis, but it's not. Okay? The loudness of a sound is related to the logarithm of that ratio of the measured intensity I to a reference intensity I sub 0. The loudness L of a sound is measured in decibels and can be determined using that formula. During an international soccer tournament in 2010, a noisemaker called the, anyone know how to pronounce that? Vuvuzela? I think that's what it is. Yeah, if you ever watched like soccer World Cup, like the fans all have them, and it sounds like mosquitoes. Like everyone's blowing on these things, and it sounds like mosquitoes. Like the whole stadium. It's crazy. So it had a measured loudness of 127 decibels at full volume. If the intensity of the sound is 5,000 times greater than the intensity of the sound of a lawnmower, then the measured loudness of the lawnmower to the nearest decibel is what? So we did questions like this, and it talks about the fact that the intensity of the sound of the vuvuzela is 5,000 times greater. And that means that if you take one sound level and divide by the other, the answer will be 5,000 because it's 5,000 times greater. And so because of that, we have to use the quotient law of logarithms. This is a logarithmic function. We have to use the quotient law of logarithms because quotient is division. But remember, the quotient law of logarithms actually involves subtraction. So we did questions like this before in our notes. So here's the expression we're going to use. It's going to be L2 minus L1. And again, we're using that because the quotient law of logarithms involves subtraction. So L2 would be 10 log, and I don't need to put base 10 there because if I leave it as a blank base, we know that means base 10. So that would be intensity 2 over I sub 0, and that'll be minus 10 log intensity 1 over I sub 0. Now, we know the sound level of the vuvuzela. Vuvuzela? Sure. You got me convinced. Okay. Can you find the sound, though, and turn it up so everyone can hear it? I would do a Google search of that at the World Cup, that sound at the World Cup. Okay, here's one from the World Cup. Of course, we got for the whole match. These people blow on these damn things. So, like I said, it sounds like a herd of mosquitoes, right? Okay, so we know that the measured loudness of the, can you say it again? Vuvuzela is 127 decibels. So that's L2. 127 minus L sub 1 will equal. Now on that right side, I'm going to simplify this equation. I can take out a common factor of 10. And that'll give me log of I sub 2 over I sub 0 minus log of I sub 1 over I sub 0. And because you're subtracting logs with the same base on the right side, we can use the quotient law to combine them. That'll be the log of I sub 2 over I sub 0 divided by I sub 1 over I sub 0. And so we're dividing by a fraction inside the brackets. So we can do that then by multiplying by the reciprocal. So it'll be I sub 2 over I sub 0 times I sub 0 over I sub 1. And the I sub 0s will cancel. So we have 127 minus L sub 1 equals 10 times the log of I sub 2 over I sub 1. And we are told that the sound of the vuvuzela is 5,000 times greater than the sound of the lawnmower. So that number, 5,000, represents I sub 2 over I sub 1. It's how much more intense one is compared to the other. So that 5,000 represents I sub 2 divided by I sub 1. Whoops, try that again. That should be 10 log 5,000. And now we can solve for L sub 1. So on the right side, we can get the value of that expression. 127 minus L sub 1 equals 10 times the log of 5,000. And again, that's a common log. So we don't have to worry about the base. So that's 36.5 99 approximately. We'll subtract the 127 from both sides, and that's what negative L sub 1 will equal, negative 90.01. So L sub 1 will equal 90.01, or approximately 90 decibels, which is why C was the answer. Okay? So we saw questions like that before as we went through our notes. In the process of factoring the polynomial p at x, a student rewrites p at x as a product of two factors where one factor is x minus 2. What is the remaining factor? So because you started with a fourth degree, if you take an x minus 2 factor out, you're going to be left with a third degree, which all four of our choices are. So the nice thing about this is they've already given us one factor. We can use synthetic division to find out what the cubic factor will be. So when we did this, we normally changed it to x plus 2 so we could add as we went along. But remember, there's two things you always have to make sure before you use synthetic division. Number one, the terms have to be written in order of descending power. But secondly, if there's any powers missing, they have to be included with coefficients of 0. There is no x squared term in p of x, so we have to write as 0x squared plus 1x minus 42. Guaranteed, one of the four answers here would be the coefficients if you forgot the 0. 1 times 2 is plus 2, and we're adding. 2 times 5 is plus 10, and we're adding. 2 times 10 is plus 20, and we're adding. 2 times 21 is plus 42, and we're adding. So these numbers give us the coefficients of the quotient, the next factor, which is 1x cubed plus 5x squared, so we can cross off C and D, plus 10x plus 21. B is the answer. Okay? Number 5 of the numerical response. For the polynomial function p at x, you can see you're missing k, the coefficient of x. Two of the zeros are negative 1 and negative 2. It can be determined that the largest zero of this function to the nearest tenth is what? Well, we would use the remainder theorem for this. If negative 1 is a 0, that means that x plus 1 is a factor. It means that when you divide by x plus 1, you'll get a 0 remainder. But the remainder theorem tells us that if negative 1 is a 0, then p at negative 1 will equal 0. That's the remainder theorem. So if we say that p at negative 1 equals 0, we can write an equation letting x equal negative 1 and the whole thing equals 0. So that's what we're going to do here. So I'll have 2 times negative 1 to the 5th plus 3 times negative 1 to the 4th minus 10 times negative 1 cubed minus 21 times negative 1 squared plus k times negative 1 equals 0. Negative, whoa, bless you. Negative 1 to the 5th is negative 1 times 2. Negative 1 to the 4th is positive 1 times 3. Negative 1 cubed is negative 1 times negative 10. Negative 1 all squared is positive 1 times negative 21. Negative 2 plus 3 is 1, plus 10 is 11, minus 21 is negative 10, minus k equals 0. And so k equals 10. So now we need to find the largest zero. Now that we know what k is, you could simply put the equation into the calculator and see where the 3x, or excuse me, 5x intercepts are. We want the largest one. So 2x to the power 5 plus 3x to the power 4 minus 10x cubed minus 21x squared plus 10x. Zoom 6, and the largest x-intercept will be the largest zero. So second function trace, we want to find the zero, which number 2, and I will go between left boundary of positive 2 and positive 3, and it is to the nearest 10th. Let's see. So to the nearest 10th, it'll be 2.3 to the nearest 10th. Okay? Hang on a second. That should have been negative 10, not positive 10. I apologize. I was going to change things a little bit. It should have been negative 10, not positive 10. So we'll go to y equals and change that to negative 10x. And graph it. Second function trace, number 2 for 0. My left boundary would still be at 2. My right boundary would still be at 3. And it's actually 2.5. 2.5. You got that blue package? Okay, that's what we're on, page number 8. So again, in this case, that last box would be blank. The graph of a particular function is shown below. If the equation is written in that form, what is the value of a? So we can start to build the equation. Remember that when we wrote equations of polynomial functions, there was always an initial term coefficient, whether it is in expanded form or in factored form. Because we have the x-intercept, we can write the factors. Negative 6 is an x-intercept, so x plus 6 is a factor. Negative 2 is an x-intercept, so x plus 2 is a factor. And positive 2 is an x-intercept, so x minus 2 is a factor. However, because the graph bounces off the x-axis at 2, that 0 has a multiplicity of 2, which means the factor has a multiplicity of 2. You need 4 factors here because it's a 4th degree polynomial. There are 4 x-intercepts. 2 of them are identical, 2 of the 4, but there are 4 x-intercepts. Remember, the number of x-intercepts is tied to the degree. The number of x-intercepts as a maximum will equal the degree. It's possible to have fewer x-intercepts than the degree, but not more. So there's the equation in factored form. We need to find out what a is, and that can be done using the y-intercept, which is 0.96. Y is 96 when x equals 0. 0 take away 2 is negative 2. All squared is 4. So 96 will equal 48a, and dividing both sides by 48, a equals 2. So it doesn't matter whether it's in factored form or expanded form, it won't change the fact that that initial term coefficient will be positive 2. So B was the correct answer there. Next question. The graph of y equals the root of f at x has a range of 0, 9 as shown below. If the original function f at x is a quadratic function, then a point which cannot be on the original graph of f at x is what? So remember, all these points here on this graph came by taking the square root of the points on the original graph, the square root of the y values. And so because you're taking the square root of y values, the y values cannot be negative. They can only be positive. So again, f at x is a quadratic function, then a point which cannot be on the graph of y equals f at x, which would be the original graph. Also, the fact that the range here is from 0 to 9, so that's the range that might come into play as well. I'm just having a brain cramp here. F at x is a quadratic function, then a point which cannot be on the graph of y equals f at x. This is the graph of the root of f at x. Okay. So it's possible for points on f at x to be negative. That is true. All it means is that when you have a negative point on the graph of f at x, it won't work when you take the square root of that. But these doesn't change the fact that you can still have a negative value of y on f at x. Okay? So the first one says the point negative 14, negative 63. So that could work. And here's how we know. Right? This graph has a domain that looks to be somewhere around negative 10 and goes up to somewhere around positive 7. Okay? So that would mean that on the original graph of f at x, all the y values for x values between negative 10 and positive 7 have to be positive. They can't be negative. That's what that tells us. Any value outside of that graph will work. For example, if a, using the point negative 14, negative 63, you cannot take the square root of that value of negative 63. So all that means is that there will not be a point on the graph that's in front of us that has an x value of negative 14. So this point is possible. The next point we have to look at is negative 7, 56. Well, that point would work because the square root of 56, if you do it on your calculator, is approximately 7.5. So when x is negative 7, which is about right here, our y value is somewhere around 7.5. So that point does work. The next point on here is the point 4, 90. So it is possible to have an x value of positive 4 because that is a point on the graph of the square root function. When you take the square root of 90, the y value is greater than 9. That doesn't work for this graph. When x is 4, we should get a y value between 6 and 9, not greater than 9. So this is the answer. D works because if this is a point on the original graph, when x is 9, y is negative 40, you can't take the root of negative 40, so there will not be a point on the square root function where x equals 9, and there isn't. Right? So that's why C is the answer. Okay. Next question. The graph of that function has a point of discontinuity at m, comma n. What is n? Remember that a point of discontinuity occurs when you factor the rational function and one of the factors cancels. So that means we need to factor the numerator. And the second factor either has to be x plus 4 or x minus 4 because it has to cancel with one of those factors on the bottom. And it's going to be x minus 4 because when you write 3x plus 1 and x minus 4, the outer products are negative 12x plus 1x gives you the negative 11x. So the x minus 4's cancel, and you're left with 3x plus 1 over x plus 4. Because the x minus 4 cancels, that tells us that we have a point of discontinuity at x equals 4. Because there's still a denominator of x plus 4, tells us that the vertical asymptote would be at x equals negative 4. So to find out what the y value is, we let x equal 4 in the simplified expression. 3 times 4 is 12, plus 1 is 13 over 8. So D is the correct answer. That's the y value. Okay, on to the next page. We've got graphs of g and h below. Each function is transformed into the square root functions, respectively. The question wants to know the number of invariant points on the original graph and its transformed graph for each of the 3 diagrams is what? How many invariant points are there? Remember that when you go from a function to the square root of a function, the invariant points occur where y equals 0 and y equals 1. You're taking the square root of the y values. The square root of 0 is still 0. The square root of 1 is still 1. The first graph will have 2 invariant points where y equals 1 and 2 invariant points where y equals 0. So that first graph will have 4 invariant points. The second graph will have only 1 invariant point. Nowhere on that graph does y equals 0, and there's only one spot where y equals 1. So the second graph will have 1 invariant point, and the third graph will have no invariant points, because nowhere on the original graph does y equals 0 or 1. So your answer here is 410. So you leave the last box blank. Use the information for 14. Again, you've got a rational function. It asks where the vertical and horizontal asymptotes are. Well, the 3x minus 2's would cancel. And this is how you find where the vertical asymptote would be. You still have a factor of negative x plus 1 on the bottom. If you make that equal to 0, add x to both sides, the vertical asymptote will be at x equals 1. So we can cross out A and C. To find the horizontal asymptote, you look at the degree of the top and the bottom. They are both quadratic functions. The initial term on the top, if you multiply out those brackets, will be 6x squared. The initial term. And that's all you need to look at for the horizontal asymptote. I mean, there's a bx and there's a c there, but all we care about is the initial term coefficient. When you multiply out the brackets on the bottom, the initial term will be found by going negative x times 3x. That's negative 3x squared. Again, there will be a bx and a c, but all we care about are the initial terms. Because when the degree of top and bottom are the same, the horizontal asymptote is found by just dividing the initial term coefficients. So the horizontal asymptote will be at y equals negative 2. And that's why D is the correct answer. Okay, so I'm going to stop there for today. You can continue to work on this package. Again, the answers are at the front, and tomorrow we will finish off this package. Okay?